Hello everyone, welcome to this lecture. The plan for this lecture is as follows. In this lecture, we will introduce the basic rules of counting, namely the sum rule and product rule, and we will discuss about the pigeonhole principle. So we will start with the problem of counting, and counting is a very fundamental problem in discrete mathematics. The reason is that in discrete mathematics, we are dealing with discrete objects, right? And since the objects that we are dealing with are discrete, we can count them. So very often we will encounter questions like how many, right? And our main aim is to come up with methodologies to address those questions. So we will introduce some basic counting rules in this lecture. So the first basic rule is the product rule, and I'm sure all of you are aware of this product rule. So let me demonstrate the product rule first with an example. So here the problem description is the following. You have two employees, say employee number 1 and employee number 2, and they are going to join our office, and there are three office space available. So I call it office 1, office 2 and office 3. So three rooms are available, and our goal is to identify in how many ways we can allocate disjoint offices to these two employees. Okay, so pictorially, these are the various ways in which I can assign disjoint offices to employee number 1 and employee number 2, right? So I can assign office number 1 to the employee 1, and given that I have assigned office number 1 to the employee 1, I cannot assign the same office to the second employee because they need to be allocated disjoint offices. So I can either allocate office number 2 or office number 3 to the employee 2, or I can assign office number 2 to the employee 1, but in that case I cannot assign office number 2 to the employee number 2, in which case I can only assign office number 1 and office number 3 to the second employee. And similarly, I have an option of assigning the third office to the employee 1, in which case I have the options of either assigning office number 1 or office number 2 to the second employee. So in total we have 6 ways. But if you see here closely, what's happening is we have a task T, a bigger task. In this example, the task T was that of allocating disjoint offices to the two employees, and we can break that task into a sequence of two subtasks, subtask 1 and subtask 2. Subtask number 1 basically requires allocating office space to the first employee, and subtask 2 is the problem of allocating office space to the second employee. And in this, say, and suppose n1 is the total number of ways in which we can solve the subtask 1. So in this example, there are three ways. Either I can assign office number 1 to the first employee, or office number 2 to the second employee, or office number 3 to the second employee. So there are three ways of solving the first subtask. So n1 is 3 in this case. And for each of these ways of solving the first subtask, I have n2 ways of solving the subtask 2. So for instance, in this example, once I have assigned office number 1 to the employee 1, I have the option of either assigning office 2 or office 3 to the second employee. So corresponding to this method of solving subtask 1, namely that of assigning office number 1 to the first employee, I have two ways of solving subtask 2, right? So n2 is 2 here. Okay. In the same way, if I consider the method of assigning office number 2 to the second employee, then corresponding to this way, I have two ways of solving subtask 2, right? And in the same way, corresponding to the method of assigning office number 3 to the first employee, I have two ways of solving the subtask T2, right? So if this is the case, then I can say that the total number of ways of solving the overall task or the bigger task is n1 times n, right? And that's why in this case the answer, namely the total number of ways of assigning the office space, disjoint office space to the two employees is 6, right? Because n1 is 3 in this case, because I can either assign office number 1 to the first employee or office number 2 to the first employee or office number 3 to the first employee. So there are three ways, and for each of these three ways I have two ways of solving the subtask 2, and that's why the total number of ways of solving the bigger task is n1 times n2. So that's a product rule. So in this case I have considered the scenario where the task T was divided into two subtasks, but in general, the product rule can be applied even for cases where your task T can be divided into subtasks T1, T2, and like that, m number of subtasks. Okay, so if you have n1 ways of solving subtask T1, and for each of these n1 ways you have n2 ways of solving subtask 2, and for each of these ways of solving subtask T1 and T2 you have like that ni ways of solving Ti subtask Ti, and like that you have nm ways of solving subtask Tm. Then the total number of ways of solving task T will be n1 times n2 times n3 times n. That's a generalized product rule. So now let's see some examples of product rule. So suppose we want to count the number of possible functions from a set A to a set B. And my set A has m number of elements, which I am denoting as A1 to AM. And my set B has n number of elements, namely B1 to Bn. So we have already answered this question when we discussed functions, but now let's see how exactly product rule is applicable to solve this problem. So your bigger task is to find out the number of functions here, and the bigger task is basically to assign images to each element from the set A. But now I can divide that bigger task into subtasks. Namely, I can identify the subtask Ti, which is that of assigning an image to the element Ai. And it's easy to see that the subtask Ti can be solved in n ways, because if I consider the element Ai, then its image can be either B1, or its image can be B2, or its image can be Bj, or its image can be Bn. So there are n ways of solving the subtask Ti, and each of these subtasks are independent, right? So that's why the total number of ways of solving the bigger task, namely that of assigning an image to each of the elements from the set capital A, is n into n into n, m number of times, and that's why the total number of functions will be n power m. Now let's see another example, namely we are interested to find out the total number of bit strings of length n. And there are plenty of ways to come up with an answer for this question, but let's see how we can apply the product rule here. And what we will do here is, instead of counting the number of bit strings of length n, let's see a related problem, namely finding the number of binary functions, namely the number of functions from a set A consisting of n elements to a set B consisting of only two elements, namely 0 and 1. And from the previous exercise here, we know that the number of possible binary functions will be n power m. So it will be Yeah, so it will be n power m here. So the notations are actually swapped here. So we have n elements here and b is equal to 2. So a1 can have two possible images, either 0 or 1. A2 can have two possible images, either 0 or 1. And similarly, an can have two possible images, either 0 or 1. So that's why we have 2 into 2 into 2 n number of times, namely 2 power n possible functions. But our goal is to find out a number of bit strings of length n. But what we have counted here is the number of binary functions. So what we are now going to do is we will show here that the problem of finding the number of bit strings of length n is equivalent to finding the number of binary functions. Namely, we can show that there exists an injective function from the set of bit strings of length n to the set of binary functions. And it's also easy to see that we can establish an injective function from the set of all possible binary functions to the set of binary strings of length n. And since we have established injective functions in both the directions, that shows that the number of bit strings of length n is exactly the same as the number of binary functions. And the number of binary functions is 2 power n. So if you are wondering what are the injective functions here, so consider you are given a binary string of length n, some arbitrary binary string of length n, say 0, 1, 0, 1, like that. Okay. Then the corresponding binary function is the following. The mapping of a1 is 0. The mapping of a2 is 1. The mapping of a3 will be 0. The mapping of a4 will be 1, and so on. That's the corresponding binary function. Whereas if you want to go from a binary function to a binary string, just we do the reverse thing. So imagine you are given a binary function, say where a1 is mapped to a bit b1, a2 is mapped to a bit b2, and like that an is mapped to a bit bn. Then the corresponding binary string will be b1 to bn. That's the injective mapping in this direction, right? So that shows that the number of binary strings of length n is same as the number of binary functions. Now let's consider another fundamental counting rule, which is the sum rule. And again, let me demonstrate it first with an example. So imagine you have a set of students in a university and a set of faculty members. Of course, they are disjoint because you can't have a student who is also a faculty member. And our goal is to find out the number of ways in which we can form a committee of just one member. That one member can be either a student or a faculty. There is no restriction. We are just interested to find out how many distinct committees consisting of one member we can form. And it's easy to see that there are 12 ways. Why 12 ways? Because I can have a committee which consists of only a student, and it could be either this student or this student, third student or the fourth student or the fifth student or the sixth student. Each of them is a distinct committee. Or I can have a committee which has this faculty member or this faculty member or this faculty member, this faculty member, this faculty member or this faculty member, each of which will be a distinct committee. So there are 12 different committees which we can form here. So now how we can view this as a counting rule. So the rule is the following. You have a task T which can be done either in one of the n ways, n1 ways, or in one of the n2 ways. Okay. Then, and of course, okay, so there is another restriction, and a case here is that none of the n1 ways is the same as the n2 ways. So for instance, if you take this example, n1 ways is correspond to the case when the committee consists of a student, and n2 ways correspond to the case when the committee consists of a faculty member. And both these cases are disjoint. You can't have a committee member which is simultaneously a student as well as a faculty member. Okay, so if both these two conditions are satisfied, then I can say that the total number of ways of solving the task T is n1 plus n2. Of course, in this case, I have considered the scenario where the task T can be divided into two disjoint cases. If you have multiple disjoint cases, then I can have a generalized sum rule. So we have now seen two basic counting rules, but it turns out that we encounter scenarios where we have to combine both these two rules. That means we can encounter problems which will require us to apply both the sum rule as well as the product rule. So let me demonstrate an example. So suppose we are interested to find out the number of passwords of length either 6 or 7 or 8 characters. That means the password can be either of length 6 or of length 7 or of length 8. And the restriction is that each character can belong to the set A to Z or the numerics 0 to 9. That means the characters could be your English alphabets or digits. And we also want passwords to have at least one digit. So these are the various requirements on the password. So it should be of length either 6 or 7 or 8. The characters should be either English characters or digits, and the password should have at least one digit. And we are interested to find out how many such passwords we can have, right? So again, this is a very common problem we encounter. So for instance, if you consider net banking password, then we have certain restrictions on the net banking password, right? It should be of at least this much length. It can be at most of this much length. It should have some special character. It should not have this. It should have that, blah, blah, blah. So in that case, one can often ask how many such valid passwords we can form. So let's see how we can apply the sum and the product rule in this particular example. So our password, the set of all valid passwords, I am denoting it as the set P. And this set P actually can be divided into three disjoint subsets. The subset P6, which is the set of all valid passwords of length 6. By the way, I valid, I mean that it has at least one digit and all the characters belong to this set. That's what I mean by valid in this explanation. So my P6 is the set of all valid passwords of length 6, P7 is the set of all valid passwords of length 7, and P8 is the set of all valid passwords of length 8. And it's easy to see that these three sets are disjoint. And by the sum rule, I can say that the set of valid password, its cardinality is same as the cardinality of the set P6 and P7 and P8, right? And there is no overlap. You can't have a password which is simultaneously of length 6 as well as length 7 as well as of length 8. So that's why we can apply the sum rule here. Now how do we find the cardinality of the set P6, P7 and P8? So let's see the logic of counting or finding the cardinality of the set P6. The same logic is applicable to find the cardinality of the set P7 as well as the cardinality of P8. So what exactly is the set P6? The set P6 is the set of all valid passwords of length 6. That means it should have exactly 6 characters, which could be either English characters or the digits, and it should have at least one digit. So it can have one digit, or it could have two digits, or it could have three digits, or it could have four digits, it could have five digits, or it could consist of all 6 digits. All these are valid passwords. So you might be tempting to apply the sum rule here, but it turns out that if I apply the sum rule to find the cardinality of the set P6, then there might be some overlaps which I have to take care of. So instead, what I can do here is I can apply the following logic. The cardinality of the set P6 is nothing but the following. It is the difference of the following two sets. You take the set of all strings of length 6. When I say all strings of length 6, that means they have 6 characters, but those 6 characters may or may not constitute a valid password. So for instance, I may have a string of the form A, A, 6 A's belonging to the set of all strings of length 6. But this is not a valid password because it does not have a digit, which is a requirement for a valid password. So that's why the set of all strings of length 6 have both valid passwords of length 6 as well as invalid passwords of length 6. Now from this set, if I subtract the set of all invalid passwords of length 6, and by invalid passwords of length 6 I mean strings of length 6 which do not have any occurrence of a digit. Those will be the invalid passwords. So if I subtract those strings from this set, then it's easy to see that I will get the cardinality of the set P6, right? So now, what's the cardinality of the set of all strings of length 6? Well, it is 36 raised to power 6, and this I get by applying the product rule. Why 36 raised to power 6? Because I have 6 positions to fill. That means I can identify 6 subtasks, and at each position I have 36 options. I can either fill a character, English character, so 26 possibilities, or I can fill any of the 10 digits, right? So imagine you have 6 slots here. Okay, at the first slot, I have 36 options to fill. At the second slot, I have 36 options, and like that, at each of the slots, I have 36 options. So that's why 36 raised to power 6. And what's the cardinality of invalid passwords of length 6? It is 26 raised to power 6. Because here, I am interested to find out in how many ways I can fill 6 slots such that none of those 6 slots is occupied with a digit, because then only that string of 6 characters can be considered as an invalid password. So I have 26 options now for each slot because I can't fill any slot with a digit. So that's why I have 26 raised to power 6 options. So again here I am applying the product rule, and now if I subtract 26 raised to power 6 from 36 raised to power 6, that will give me the cardinality of P6. The same logic you can apply to find out P7, and similar logic you can apply to find out P8, and if you sum those three quantities, that will give you the required answer. Now let's see another interesting counting rule which we encounter very often in discrete mathematics, and this is called pigeon-hole principle. So what is the scenario here? So in this example you have 13 pigeons and you have 12 holes, and suppose the pigeons are going to randomly occupy these 12 holes. We don't know in what order they will be going and occupying these holes. But irrespective of the way they are going to occupy these 12 holes, we can say that there always exists at least one hole which will have 2 or more pigeons. A very simple common sense, right? And how we can prove that? We can simply prove it by contradiction. The contradiction will be if each hole is occupied by exactly one pigeon, then since we have 12 holes, we get 12 pigeons, but we have 13 pigeons. So that automatically implies definitely there will be one hole which has more than one pigeon, right? So very simple common sense. So now how do we generalize this rule as a counting principle? So the generalized pigeon-hole principle is the following. So imagine you have n objects. In this case, you had n pigeons. And suppose those n objects are assigned to k boxes in a random fashion. Then the pigeon-hole principle states that there will be at least one box which will have these many objects. So this notation is called as the seal notation, right? And what basically this seal notation says is if you have a seal of say 2.3, then sealing of 2.3 is basically the integer 3. That means if you have, so what you do basically is you take the integer which is higher than the integer 2 here. That will be the ceiling of 2.3. The ceiling of 2.1 also will be 3. Basically, you take the next integer, which is a complete integer, and larger than the current number. Whereas the ceiling of 2.0 will be 2 only. So, in this example, if I apply the generalized pigeonhole principle, it basically says that there will be at least one box with 13 over 12 pigeons, and 13 over 12 will be a real number, 1 point something something. And if I take the seal of that, I will be take the next higher integer, which is 2. Right. So the proof is by contradiction. So let's see an application of pigeonhole principle. So what we are now going to show is a very interesting result. So imagine you have 6 people present in a party, okay, and it is guaranteed to you that you take any pair of individuals, then they will be either friends or enemies, right? You don't know what exactly is the situation because the party consists of 6 random people, but whatever whichever 6 random people are there in the party, it is guaranteed that you take any 2 people in that party, they will be either mutually friends or enemies. Then our claim is the following. Our claim is that irrespective of the way the people are mutually friends or enemies, there always exist either 3 mutual friends in the party or 3 mutual enemies. One of these two will definitely be the case. So how we are going to prove this? We are going to prove it by applying the pigeonhole principle and various other proof mechanisms. And remember, when I'm making this claim, the claim is irrespective of the way those 6 people are friends or enemies with each other. It might be the case that all of them are mutually friends. Then automatically the claim is true. It might be the case that none of them are friends with each other. Then again the claim is true. The claim is if you have 6 people, definitely one of these two cases will always hold. So how we are going to prove this? So we will consider an arbitrary party consisting of 6 people, and out of those 6 people, let's randomly choose one person. So we are now left with 5 people, right? So what can I say about those remaining 5 people? By pigeonhole principle, I can say that out of those remaining 5 people, at least 3 people will be mutually friends with this person that I have chosen, or there will be 3 friends, or there will be 3 people who are enemies, mutually enemies with this chosen person, right? I don't know what exactly is the case because that depends upon the exact uh, way in which the persons or the people are mutually friends or enemies in the party, but irrespective of the case, one of these two will always hold because I have 5 people, right? And I can't have, so even if out of those 5 people, say 2 are friends with this person and 2 are enemies with this person, I am left with one person who has to be either a friend or has to be an enemy with this person. That's a simple logic, right? So that's what I'm saying here. So you have 2 possible cases. So what I can say is the following: without loss of generality, imagine that out of those remaining 5 people, there are 3 people who are friends with this person. And since I am applying this argument without loss of generality, the same argument can be applied for the second case as well when there are 3 people who are enemies with this person, right? So again, since there are 3 persons who are friend with this person, I'm taking any 3 person here, right? Who are friends with this fixed person. Now my claim is not yet proved here because individually these 3 people are friends with this person. That does not mean that I have the existence of three people who are mutually friends with each other. That means they all have to be friends with each other. That's not guaranteed as of now. As of now, I have just guaranteed that this person is a friend with this fixed person, second person is a friend with the fixed person, and the third person is a friend with the fixed person, right? So this notation basically denotes friendship. Now I can say that the following two cases hold. The three people who are friends with this fixed person, they can be mutually enemies. That means these two are enemies, and these two people are enemies, and these two people are also enemies, right? So, okay, so let me, these two are enemies, these two are enemies, and these two. So, if this is the case, then I got three people who are mutually enemies with each other, and my claim is true. Okay, whereas I can have a second case where those three people, they are all not mutually enemies, but there exists a pair among those three people who are friends. Say the first two people are friends with each other. Then I got three people who are all friends with each other. And this proves my claim. Okay. So now you can see I have proved my claim irrespective of the way that six people would have been friends or enemies. Now the question is, what's the speciality of the number six here? Right? I took I proved my claim for the case when there are six people in the party. What if there would have been five people in the party? Then can I say that irrespective of the way those five people are mutually friends or enemies, I will always have either three mutual friends or three mutual enemies? And the answer is no. The claim is not true for the case when there are five people in the party. So consider the case when I have uh, these five people, and there is a fixed person, okay, who is friends with this person, but he's not friend with this person, who is not friend with this person, and these two people are friend with each other, these two people are friend with each other, and so on, right? And these two people are friend with each other, and so on. So in this case, you can see that among these five people, I neither have the presence of three mutual friends nor I have the presence of three mutual enemies. So for instance, if I take these three people, then this this girl is a friend with this person, but that girl is not a friend with this person, right? Whereas I require for my claim all the three people to be mutually friends or mutually enemies with each other. So when there are five people in the party, my claim is not true. So now let's generalize this example to a beautiful theory of Ramsey numbers. So I define this function r of m comma n. So this function r is attributed to Ramsey, who invented these numbers, and here m and n are greater than or equal to 2. So what exactly is the value of the Ramsey function r of m comma n? It is the minimum number of people, I stress, the minimum number of people required in a party such that you either have m mutual friends or n mutual enemies, irrespective of the way the people are friends or enemies with each other in that party, assuming that every pair of people are either friends or enemies. Okay, so for instance, what we have demonstrated is that r of 3 comma 3 is 6. Why 6? Because only when you have six people in the party, then you can claim that you will either have the presence of three people who are all friends with each other, or you will have the existence of three people, none of whom are friends with each other. R of 3 comma 3 is not 5, right? It's not 5 because we had given a counter example. Namely, we can have a scenario where we have 5 people in a party such that we neither have the presence of 3 mutual friends or 3 mutual enemies. So, so it turns out that even though this function is well defined, we do not have any generic formula to find out the value of the Ramsey number or the output of this Ramsey function R of m comma n for any given value of m and n. It's only for certain values of m and n that we can compute the value, but there is no pattern or relationship or any observation which is there in the output of the Ramsey function, due to which we do not have any generic formula. Okay, so that brings me to the end of the today's lecture. These are the references used for today's lecture. Just to summarize, in this lecture we started our discussion on counting. We introduced two fundamental counting rules, namely the sum rule and the product rule, and we also discussed the pigeon-hole principle. Thank you.